Hello YouTube, WF7i Homebrew here. So I just wanted to do a little video today to kind of continue to expand on what I did yesterday. Um, it's kind of late at night, so I don't think I'm going to do any building tonight. So I thought I would just kind of shoot a little video showing the circuit in a little bit more detail. So this is one oscillator. I'm going to build 3 oscillators. And so for some of you, this is very basic. Maybe it's not very interesting. Others have never built an oscillator before. And what I'll say is I find oscillation really fun and kind of fascinating. And it's strange, but sometimes these simple circuits are harder than you would think. They don't always oscillate just because you follow a schematic. Sometimes things don't work the way you think they should. So whenever you get a strong oscillation, to me it's always kind of a thrill. It's kind of fun, and it's radio. It's generating electromagnetic energy, and when you can do it with just a few components, you're not using a chip with a million transistors, a computer, an SDR. This is not an SDR. This is what another blogger I used to listen to would call hardware-defined radio, not software-defined. This is kind of old school. So this is a very basic kind of Colpitts oscillator. And what it is it's a little messy looking, but I'll explain kind of some of the parts of it here. So this is for 20 meters, and it's this circuit here. This up here is a different part of a different circuit. So the 3904 is the bipolar junction transistor, just a simple garden variety transistor that probably a lot of us have hundreds of them in our junk boxes, very cheap. And one of the keys to getting this to work right, so there's a couple things. You got to bias the transistor. So I have a 1K resistor here and a 33K resistor here between collector and base. 1K is between emitter and ground. That just establishes the bias point of the transistor. And that, we can do more analysis and explain how that works, possibly, but I would just suggest you look it up on the internet if you want to know more. There's plenty of engineering textbooks. But you want to set a bias point so that, the squiggles of the back and forth AC waveform don't either exceed your supply voltage rail or, go, too far to the negative side. And you want to have this kind of wiggle room, so to speak, so that your AC waveform is kind of centered within the bias region. And without doing a lot more analysis, it's kind of hard to explain it beyond that. But if you don't bias it properly, you can sort of have it hit the rail, and you'll start getting clipping and stuff like that on one end or the other of the sinusoidal waveform. I didn't really design this circuit, to be honest. This is one that, it's published in many different publications. You can find it online. These choices for resistors are not that special. The one thing that is a little bit special are these 2 capacitors. So in order to get the oscillation, you kind of have to set up a phase shift of some sort. You have, kind of this 90-degree and 180-degree phase shifts going on. And what I did is experimentally determine what these capacitors should be. And I tried different ones, kind of started out with what I found published in, one of my books, a couple of my books that I have here. You have ARRL Handbook. I've got Experimental Methods in RF Design. I've got a BFO circuit made by Doug DeMoss for 455 kilohertz IF. And they all used various different types of Colpitts oscillators. So I kind of started there, but I found out that if I, change those values around, I could get much stronger oscillations. If I use the wrong value, for instance, if I put 600, 800 picofarads for those 2, oscillations would be much lower in amplitude, and eventually it just wouldn't oscillate at all. If I got really crazy values in there. So I found that these 2, 180 and 180, gave me the peak amplitude. This 270 picofarad sort of couples this oscillator to the tank circuit over here. We call it the tank circuit. It's kind of, this whole thing is really part of the tank circuit, I guess you could say. So this is the coil. So it's an LC parallel parallel LC oscillator. So you have your inductor L1. I forget how many turns that is. I think it's a 7 or 8 turns. And I forget what the, I'd have to look it up again. I think it's like a T50-1 toroid core. Let's see, T50. I think that's right. Or T50 dash. It might be a T50-2. Anyway, eventually, what I'm going to do is put this formally together into a schematic diagram on a using a nice, I think it's Eagle. I have Eagle CAD, and I can draw this up and put the values, and I'll put it on a blog so that people can refer to this. So these are just my notes right now on an engineering paper as I went along. But it's 5 or 6 turns on this toroid. Gives me about, I think it was about 2 microhenries or 1.8 or something like that microhenries. And then this whole mess over here are experimentally determined values of capacitors. And actually this series value of 230 is a couple different capacitors as well combined to make the 230. So both this series and these parallel combinations were experimentally determined to figure out what my frequency range would be for the oscillator. What's not shown here, so where it says 3 and there's a little dot, well 3 comes up here and this goes to my band switch, so 80, 40, or 20. So right now it's at 80, so it comes down here, and I've got some more capacitors. So this is my main variable tuning capacitor here. It goes from 20 to 400 picofarad. Then I got a fine tuning capacitor. Its range is 12 to 150, and I put a little trimmer kind of capacitor, about 6 picofarad. So when you put the 6 pico in series with this 12 to 150, what ends up happening is when you vary this one, you're not varying from 12 to 150. You're really varying just, I think it's like 5 or 6 picofarad is the combination here when you do the math combining these two in series. So it's a very, very small variation in capacitance. So that tiny variation in capacitance in parallel with the main capacitor means that you're fine-tuning basically this main capacitor, because this one's a pretty big range. And when you're trying to tune 20 meters, this will jump around pretty fast, and it's very hard to tune in a sideband signal with a real coarse tuner. So there's different ways around that. I mean, I know there's like a reduction drive type knob that you can get for these variable capacitors, and that would tune much slower. So there's a million different ways to approach this. And another way, of course, is you don't have to use a tank circuit. You don't have to use LC. What you could do is use a lot of circuits like this will use a varactor diode for the capacitor. And so you'll have this kind of reverse biased diode over here to provide your capacitance, and you just have a pot, a variable resistor, and you apply voltage across this reverse biased varactor diode, and you vary it with your pot, how much current goes through that diode, and you can vary the reverse bias on that varactor. And by varying it, you're changing what they call the depletion region in that diode, which is kind of like a capacitor. It's kind of like you can think there's 2 plates of a capacitor, and as you vary that reverse bias voltage, the plates get it further apart or closer together. That's kind of how you can think of it. And that varies the capacitor. And so there's actually no air variable capacitor. There's no mechanical parts with that. And that's a very nice way to go, actually. And I thought about doing that, but I really like the air variables. I think they're fun. I like the fact that it's a really broad range. I mean, this is a huge range of capacitance. You can tune pretty wide swaths of the band, and I just like them. I don't know. I just like air variable capacitors. To me, they look pretty old school. They're just kind of fun to do. So, but as you can see, it's a lot of work. You got to play with a lot of these little values to kind of get the range dialed in. Now, of course, probably you could say, well, why don't you just replace all these with one capacitor that's the same value? Well, in practice, when you do this kind of stuff, they don't add up quite exactly, and it's tricky. Sometimes the larger value capacitor, even though it's the same value as several of these added together, does not have the same effect, which is kind of weird, and I know there's a reason for it, and I can't explain to you what it is now. Somebody else may know. read about it before. But you get sometimes different effects when you sum together several small capacitors versus using one large one with these type of circuits. So anyway, it looks ugly maybe, but it works. It actually works pretty well, and I showed you in the last video. So as far as what it looks like, this is sort of what it looks like. And let me see if I can angle this down a little bit more. This is how I chose to implement things, and as things fall apart here. This is what they call a Manhattan style. Some of this stuff is just debris. These are pads. I don't even have these soldered down. But this is sort of the area of interest here. Maybe I can zoom in for you a little bit with my little high-tech phone here as things try to fall apart. It's kind of hard to walk you through the circuit because it's just real messy. So this is Manhattan style construction. It's kind of almost like dead bug in a way. If you look up dead bug construction, that's where you had this ground plane and you just sort of solder components with their leads sticking up out of this ground plane, and you just kind of make interconnections all over the place. So it's not quite dead bug. It's Manhattan style because the nodes, so the connections between circuit elements, are on these little pads. And these are pieces of circuit board that somebody cut up. There's a company called QRP-Me, like ME. You can buy these from, and you can look them up. QRP-Me, they still sell these. And some guy cuts up all these little circuit board pieces. And so this side you can put solder on, and this side you just put super glue on. And so you can put all these pads down on your copper-clad circuit board. That's what this is. This is a double-sided copper board. Didn't really need double-sided. Single-sided would be fine for what I'm doing. And so I soldered. It's kind of hard. Let's see if I can use, I need a little pointer stick thing. So these are the nodes. You know, this is a node here. That's the base of the transistor right here. This is the emitter. This is the collector. So these are all little pads that I glued down. These are the biasing resistors. So that's my, let's see, brown, black, orange, or red, I guess. So 1, 0, 0, 0. So that's my 1K resistor right here. That's emitter to ground. These are my 180 Colpitts sort of phasing capacitors here between emitter and ground, emitter and base. This is the capacitor, the 270, that connects over to this whole mess, which gets into the inductor. Now this is my inductor as part of the tuned circuit. One lead's going to ground down here, the ground plane, and the other lead goes back and connects to this 270 guy right here. And there's a node back behind here, so that's another node right down here. And the lighting is kind of getting weird here with the phone and everything. And this is the big mess of capacitors down here that I used to kind of tune my range. This and then the other, these are kind of the parallel capacitors, and then I have like this guy and this yellow guy are the 2 series ones that I put together. So it's kind of crazy, but it works. It works pretty well, and it seems pretty stable. And that's the one comment I'd make too, is with modern technology, you know, people are worried about, you know, getting drift down to, you know, essentially zero. And, you know, in terms of just casual listening on the bands, you know, if you're doing digital modes, that's different, I guess. Frankly, I think this is stable enough. I could probably do FT8 to a certain degree. You know, it does drift, so eventually I'd probably have some trouble with it. But, you know, it really doesn't drift that bad, and for casual listening, it's fine. And, you know, once it warms up, you can listen to a QSO for quite a while, and it's not going to be an issue. I think a lot of people feel that the older technology is just, you know, garbage, and they have to have, you know, DSPs and, you know, SDRs and all this in order to have a you know, reasonable experience listening to signals. And that's just really not true. Now, there are some really poor circuits out there. For instance, my my poor old realistic DX100 over here on the bench. Now it drifts really bad, and it's analog. I think that's just sort of, there's some poor design decisions in that radio, and I'm not exactly sure what part of it's drifting so badly. But I built this with a lot of NP0 capacitors. Somebody had commented, did you use NP0s? Yeah, all I have is NP0s. I have a big box of NP0s. So those are special ceramic capacitors that have very low drift. Now they still will, their value will still change over time a little bit, but they're very, very stable. And that seems to make a pretty big difference. I think you have to really be careful about some of the, component choices you make with some of these circuits. Especially if you're concerned about drift. And I've read things, there's people that design VFOs, and they try to get temperature coefficients that offset one another, so you can get positive and negative. So some components will drift up in frequency as they get warmer, or in value, I should say. Some will drift up, some will drift down, and then you can combine them and, basically cancel out the drifts. I'm not going to do that kind of thing, and I'm not even sure how easy it is to get a hold of those type of components anymore. So this is good enough for me. This is a fun project. I really, really enjoy it. It's not perfect, but it's good enough, I think. What remains to be done now is going to be, finishing the other two oscillator sections for 40 and 80. And then I've got to hook in, of course, the audio amplifier chip, the LM386, so I can get audio out of this thing. So the direct conversion, the signal's going to come in. It's going to mix with these oscillator signals, and it's going to mix in the difference frequency will basically be audio. So it's kind of like no difference frequency. The difference frequency is 0 to however many hertz you can hear with your ears. That's your difference frequency. And that's what's going to be amplified by the 386. It's going to go into my, I have a little port here for headphones, and you can plug in headphones or amplified speaker, and you can listen to it. I may put in a speaker. I'm not sure yet. I kind of would like a speaker, I guess. So I may play around with that and get a better amplifier and actually have a speaker on the radio. That would be kind of nice. So that's pretty much it. I guess one other little thing here, a little trick or tip. I use this as a little mounting platform for the toroid here. And what this is these are anchors for drywall screws. And I was doing some work on my house, and we had to get some of these. And so I thought, you know what? This would actually glue down on my circuit board really well. This is a very flat surface here where the little screw thing is. And then this is a nice little plastic post, non-conducting, and I could slide the toroid over this, glue it down, and that's what I did. I just glued it down like that. This thing is really rigid. It won't move at all. So things like that, I enjoy stuff like that with these little projects. It's not rocket science. There's probably a gazillion ways to do things better. They sell professionally made mounts. There's probably people out there that 3D print special things for their toroids, whatever. This was a very, very cheap part at, Home Depot or Lowe's. I think it's a few pennies probably for each of these. So, whatever floats your boat. So that's about it. It's a pretty long video. Don't know if anyone's going to watch it, but if you do, thanks for watching. Give me a thumbs up and all that kind of good stuff. Let me know if you enjoy these videos or not. I've gotten a couple thumbs up, and I've gotten a few comments. I know there's a few of you watching, and I do appreciate it. It's kind of fun to share these. If you guys have channels with videos, with radios that you want to share, let me know. I'll subscribe to you. I enjoy watching your guys' videos too. So 7 3s. Have a good one.